Okay, good morning, good afternoon, good evening. Welcome to the CG Earth Data webinar. Today is our great pleasure to have Professor Anastassia Borisova speaking with us, and this will be the last talk of the seminar for this year in our webinar series. Professor Borisova spent her early educations in mainly Moscow and Moscow State University, then PhD at the Russian Academy of Sciences. And then she moved to Brussels, Belgium, to perform her postdoc, and then she moved to France at University of Toulouse, and where she's currently a senior as a researcher. And Professor Borisova's work has been mainly on the igneous petrology, volcanology, and she's combined elemental as well as atopic geochemistry as well as experimental petrology, as she will show a little bit today on various topics. And then today she's going to talk about the early Earth topic from the terrestrial planet perspective. And I would highlight that the picture that Professor Borisova is showing here in the cover page are drawn by herself 2 years, a couple years of AGU. So that's a really impressive artwork. And I think that's also very good summarize the paper that she's going to present today. So, so Anastasia, and I'll give the rest up to you. And this webinar is relatively freestyle. So normally we ask speakers to speak for 40 minutes, but feel free to go longer or slightly shorter than that. And then we have some time for interaction with our participants who will ask some questions. Okay, so
Okay.
please. Mhm.
Okay, thank you. Thank you for inviting me for this webinar to present my work on making continental crust and water-bearing terrestrial planets. And indeed, I'm a senior scientist in working for CNRS in Geoscience Environment Toulouse. And working a lot on experimental approach on, in particular, kinetic approach. I will tell you some details today. So the planetary and geological magmas produced at depth meet the rocks at variety of temperature conditions, pressure conditions during their ascension towards the surface. Reactions occur between the magmas and surrounding rocks, but despite the potential importance for the regulation of magma differentiation, the rates and mechanism of these reactions are rarely known and even rarely considered. Now, mostly thermodynamic considerations are applied, suggesting attainment of phase equilibrium happening in a closed system. However, most magmatic processes and systems are open systems, and we should make attention on the kinetic aspects like rates, mechanism, and duration of the reactions, which are very important even at higher temperature. So the magmas and fluids are heated by a source of heat coming through the lithosphere, where a lot of reactions happens like chemical mixing, hybridization, degassing, and this we call as a lithospheric control or on the magma chemistry and the topic chemistry. And what we see on the surface is highly affected by these processes of lithospheric controlled assimilation or controlled hybridization. So my methodology uses kinetic approach and considering mechanism, rates, and duration of the processes, and this is the main approach of my current project, advanced ERC advanced grant, Planeta Physics, funded by ERC for 5 years. This is the photo of my team working on this project, and the project contains 4 work packages on the experiment, natural rock investigation, and modeling, and all concerning the first primitive continental crust production. So my talk today is based on this main topic, which is founded on series of experimental studies on the first continental crust production. How the continental crust formed through the Earth's history since Aden. How did it first form and grow through the time? This map on the right indicates of different parts of the Earth where cratonic parts can be seen and indicated by violet color. And this is cratons, where the most ancient part of the Earth present, and where the most ancient zircons and zircon-bearing rocks were recorded. What kind of processes and environment created these ancient zircons and these ancient rocks? The paradigm shift is happening today. We know from the investigation by the Curiosity rover on Mars, and also by other rovers as Perseverance on Mars, that ancient continental crustal and quartz-bearing rocks could be formed without plate tectonics, without subduction, and which is a regular environment or geological environment on Mars. So this is directly applicable to the early Earth when the mantle temperature were much higher than today. And on the right, I'm showing the environment suggested for the Ardean primitive Earth, where serpentinized rocks, greenish serpentinized rocks existed on the surface. Liquid water already existed according to our investigation of the ancient zircons. And the role of meteoritic impacts was likely very important at this stage, and some people indicated the role of mantle plumes during this environment. So what we know, of course, there are a lot of debates on the origin of the physics crust, the depth of its production, the role of plate tectonics, the subduction, and the physics magma production. And what becomes to be clear that the physics crust was hydrous, igneous, and originated rather from mixed ultramafic protocrust rather than purely mafic protocrust 4.5 billion years ago. And this physics crust production involved the hydrated protocrust, which was altered by high temperature aqueous fluid around 200 degrees. Today I will talk about mostly about how abundant was this first planetary physics crust. So the current paradigm on the first continental crust production considers a very deep and subduction-driven production of this physics crust, physics magmas, and comparable to what happened in Archean during the tonalitic, trondimitic, granodioritic series production. So the paradigm consider deep production above 1.5 gigapascal, pressure above 20, around 15 kilobars, and between 900 and 1100 degrees Celsius. However, um, uh, our consideration of the shallow mechanism now suggests that the shallow serpentinization was likely possible, and reaction between a serpentinized protocrust and basaltic intrusions could form the first felsic magma, which were likely involved in the production of the first Hadean zircons. In fact, in 2020, we discovered the felsic melts produced upon basalt serpentinite reaction and with composition corresponding to the bulk continental crust. Based on this discovery, we propose an alternative model of the origin of the primordial shallow phasic crust through the mixed basalt serpentinite reaction at shallow conditions below 5 kilobars. On the left side, you see two different configurations of the runs, the reaction between serpentinized circle and basaltic powder results in formation of the hybridic zone rich in phasic melts and olivine rich magnesium rich olivine residue, and in contact there are formation of hydrous basaltic liquids. And this reaction of serpentinite to basalt can be can be shown as formation of the phasic melts, liberation of the fluid, and formation of the high magnesium olivine due to incongruent reaction of orthoperoxene, which is dissolved with liberation of silica and formation of new phases, mineral phase, which is high magnesium olivine. So this reaction was investigated experimentally, and we use a different approach like piston cylinder press or internally heated pressure vessel. And on the right, you can see these techniques shown on the photos. So in the center, you see olivine-rich assemblage. In the interstitial zones, there are formation of the high silica melts, which with composition corresponding to the bulk continental crust. So in addition, we applied mixed configuration of the experiment where we very well mixed serpentinite rocks and basaltic powders together in different proportions. And this was applied in our last study on 1 kilobar pressure and 5-day duration and 1100 degrees. And we used also different thermodynamic methods, melts and perplex, to investigate the final products of these reactions at different pressures up to 9 kilobar pressure. So all experimentally produced melts are meta to peraluminous with different aluminum contents, but likely most of them are highly enriched in aluminum. The high serpentinite proportion, the high silica content in the phasic melts, and the experiments and thermodynamic modeling indicate that the residue was of ultramafic composition reaching high magnesium olivine and sometimes chromite corresponding to dunites, chromatites, or Garsburgites. So this mixed configuration likely corresponds to what was can be formed due to impact-induced melting of the primitive serpentinized protocrust, shown on the right with a schematic illustration of the impact-induced melting. And this impact-induced melting can be very favorable to the creation of these physic melts. So we performed different series of experiments with different serpentinite proportion at these conditions of 1100 degrees, 1 kilobar pressure, and 5 days duration. And this the schema of silica in the melts versus the serpentinite proportion. You can observe the yellow dots of experimental melts and greenish and orange and red dots for the modeling, thermodynamic modeling at 1 kilobar pressure as well. And the difference between these silica contents in the experimental modeling modeled melts corresponds to 6% of silica, which is the known content of silica in the aqueous fluids at shallow conditions. So we explain this difference by contribution of the fluid phase in interstitial melts and combined signal of fluids and melts in the interstitial glasses formed during experiment. For alumina content in the melt versus serpentinite proportion, we can observe the very good agreement between the thermodynamic data and data from experiments, and shown in the yellow dots as well. And this is likely much less solubility of aluminum in the fluid at these conditions. So, and melt fraction versus serpentinite proportion was used to constrain the maximum mass of the continental crust, which could be formed during this reaction at the primitive conditions and impact-induced melting. So at 40 and 0.4 melt fraction, we can observe the formation of the phasic melts in our system, and so we estimate the subsequent segregation of the phasic melts below 0.4 melt fraction from ultramafic residue is able to produce up to 50% of the present-day continental crustal mass at the beginning of ADN. So what is happening, how our data correlates with hafnium isotope composition of the ADN zircons? As you know, there is epsilon hafnium diagram versus the age of zircons. Different measurements of the zircons indicate the different slopes on this diagram, which is direct indication of the lutetium hafnium in the parental melt. In our melts, the lutetium hafnium was between 0.011 and 0.024, which is in excellent agreement with the data observed in our runs based on basalt serpentinite reaction. So this slope for the Ardennes zircon, which is likely mostly associated with the mafic crust development or evolution, we can associate with the mixed phasic to mafic, mostly phasic than mafic crust evolution, which is observed in our runs. So finally, our model considers the impact-induced melting of the Hadden protocrust and formation of the plagio-granitic crust in association with dunitic or Garzburgitic or chromatitic residue at the beginning of Hadden environment. And in contrast, on the B scenario, we also applied differentiation of the primitive mantle, which could exist on the first stages of the planetary evolution. And this differentiation can give us very limited quantity of the plagio-granitic crust below 1 kilometer of depth. Above 1 kilometer of depth, whereas basalt serpentinite reaction in our system can produce up to 50% of the present-day continental crustal mass. Similar scenario can happen on Mars if we and there are evidences for plagio class-rich crust in the Martian impact structures. And during the Noachian period, the formation, the impact-induced melting can provoke and induce the formation of the impact magma and differentiation to the pleasure class rich crust and liberation of lertsolithic mantle due to this differentiation, whereas in this scenario, the very limited plagio-granitic crust could be formed due to the bulk primitive Mars, silicate Mars differentiation upon the fluid saturation at the first stages of the planetary evolution. So, in conclusions, there are several papers published on the subject. You can see this paper published in Frontier in Science. There are some comments for geology paper, and there is a paper published in geology, and finally in Science Advanced paper, which is the most the last one. In conclusions, the physic melts may have been generated by shallow melting below 5 gigapascal, 5 kilobar or 0.5 gigapascal of serpentinized peridotites with basaltic magma on Hadden Earth. The chemistry of the Ardennes zircon is consistent with crystallization in phasic melts, which is similar to the modern oceanic plagio-granites. And these liquids are closer to Archean TTG or this series with Archean series rather than modern granitoids. Based on hafnium isotopic evolution of Hadden and lutetium hafnium detrital zircons and residual fluids, we know that interaction at the end of the magmatic ocean stage enables the formation of the Hadden um, crust, representing up to 50% of the present-day continental crustal mass. So serpentinized protocrust had a dual role in the primitive planetary environment to produce the continental crust, enabling the emergence of life in the environment of terrestrial planets. So this is our paradigm shift. Now you can memorize this slide, the final one, from the deep to the shallow and water-bearing system. And thank you for your attention.
Okay, thank you very much, Anastasia. Now is a questions from our participants, so feel free to open your mic to ask a question. Alternatively, you can leave your question in the chat, and then I could read the question on your behalf. Any questions? Okay, let me start from one question. It's more question from a clarification. So in the cartoon that you drawing here, just in this slide, could you explain again in the figure A1? So for the brown color, upper layer, 20 kilometer layer,
Yeah,
that is the serpentine, I suppose.
yeah, serpentinized
Mhm.
protocrust
Yeah, yeah.
affected by liquid water
Uh-huh.
from the liquid water ocean,
Uh-huh.
and then it affected by impacts of meteorites, of chondritic meteorites, and lately there is formation of impact-induced magma, which is shown in red
Mhm.
on the second
Mhm.
stage, and the third stage indicates the differentiation to the formation of the
Mhm.
less dense phasic crust and more dense ultramafic residue.
Mhm. And in figure A1, so the dikes that looks like that, the gray color you have drawn. So that's the basalts, I suppose.
Yeah, yeah,
Okay.
yeah.
Mhm.
This is
Mhm.
a mixed, our
Mhm.
scenario is a mixed protocrust composed by serpentinite together with a mafic component, which could be basaltic intrusions.
Mhm. Mhm. Okay. Okay. Thank you for clarification. Uh, Questions from our participants? Then let me ask you another one while we're waiting for other people to pose questions. So in your perspective, then, without the water, without the superintendent, we should not make any felsic. We cannot make felsic crust. Therefore, you don't think that people are going to find any of the felsic crust on the moon, for example. That is
Mm.
water depleted, very likely.
Yeah, there are different kind of mechanisms to form the phasic crust. Phasic crust can be formed without water, but to be abundant, we need this basaltic component and also the water component in the system to favorize formation of the phasic melts, abundant phasic melts in the system, and to favorize the concurrent melting, concurrent dissolution of the orthoperoxene and formation of this high silicon melt and in equilibrium with olivine.
Okay. Then let me ask you another one, and maybe
Yeah.
go a little bit beyond the terrestrial planets in the solar system. So, do you expect this is also the case for the exoplanets, as people have been observing
Uh,
nowadays, including super Earth surface?
yes, but this mechanism requires water, and the most important condition for this mechanism on exoplanets should be existence of water as well,
Mhm.
which is quite a common component in this
Mhm.
in the universe. So we can suggest this water component can be present even in exoplanetary differentiation. Yes.
Mhm. Okay, so yeah, so your work is strengthen the role of water as the crucial one. Uh, yeah, not only for life directly, but including for the, like say, the felsic product crust that could be generated. So, uh, okay, so what's next? What's next? Is this work done? Is the end of your
Yeah.
ERC grant? And I believe there are more
Yeah,
exciting things
it's huge project. So the next we'll see some influence of andritic presence in this environment and reaction.
to. Mhm.
So there are several approaches to get this information: chemical and isotopic composition, together with new experiments on the partitioning. So it's a huge work
Mhm.
which is already started, and I hope to publish all this soon. To make these results available for the all people.
Mhm. Okay. Yeah, that will be very interesting to the rest of the community for more detailed evidence, like the experiment, more evidence for that, and especially for serpenting is such a important topic that nowadays a lot of people shift their attention to that. So that will be a very valuable contribution to the community. Uh,
Yeah, we've got the Jack Hill zircons
mhm,
recently, and we're working on this by
mhm,
different very advanced methods.
mhm.
Um, yeah.
Okay. How many grains have you got? I mean,
We've
about the
got
one.
we've got just one sample, but there are huge quantity of zircons inside, so we're
Okay.
happy about. Yeah, so it will be. Now we've got as well new samples from our expedition in Australia, from another location or in close to the cochlear bore in Western Australia, and so we're working as well on these samples. Currently, they are currently in the separated from the
Mhm.
rocks, and we'll see what is going on after.
Okay. Yeah, well, that's very exciting. Uh, yeah, that's a very valuable sample, so that people don't want to lose any of those. Uh,
Yeah,
as crucial
yeah,
as those extraterrestrial samples, so that people get that people want to
yeah. It's comparable to extraterrestrial samples. You're
yeah, yeah,
right.
yeah. In terms of the value importance to mass of sample.
Yeah,
A milligram. Okay. I think that's very great, Anastassia. I think it's great. And thank you very much for your talk today. And we are going to post talk on video. I'm going to send the link to you so that
thank you.
I say other people interested can watch it. I bet that you're going to receive a lot of clicks for your video, and people are going to read more of your paper that you publish over the years. for that. Okay, I think that's the end of the talk today, and also the end of the webinar series for this year. And thanks everyone for your participation, and thanks our speaker today again. Thank you.
Thank you.